Welcome to Facts Up Daily, your daily destination for the world's most fascinating facts.
Think about the sheer gravity of this fact for just a second. The entire Apollo 11 mission, that monumental human achievement that calculated orbital mechanics, navigated the absolute vacuum of space, and safely landed human beings on the moon back in 1969, relied on computing systems that used orders of magnitude less power than the smartphone sitting idly in your pocket right now. You are quite literally walking around with a supercomputer that completely dwarfs the technology we use to conquer the stars.
Okay, let's dive into this, because tracing the genesis and evolution of digital intelligence is, honestly, one of the most fascinating stories of human ingenuity out there. We have gone from a world where one single megabyte of storage in the 1950s cost roughly $10,000 to a modern reality where that exact same money buys you massive multi-terabyte drives. We unlock our phones 50, maybe 80 times a day, completely taking for granted a digital landscape that grew from incredibly quirky mechanical roots into the massive artificial intelligence systems that are actively reshaping our world today. But before we get to the AI of today, we really have to understand the fundamental limits of raw calculation. Look at this number, 10 to the power of 80. There are actually more possible chess games than there are atoms in the entire observable universe. This staggering scale is exactly why we couldn't just build faster calculators to achieve artificial intelligence. Brute force computing alone cannot simply solve complex problems like chess by calculating every single possible move. It's just not physically possible. We had to teach machines a completely new way to process information.
Section 1. The quirky roots of tech, from moths to wooden mice.
You know, to understand how we built those teaching machines, we have to remember that the origins of our sleek, digital world are surprisingly physical and wonderfully analog. Just look at this timeline. The tools we use to interact with machines every single day were born from physical constraints. The QWERT keyboard layout you type on, it was designed in the 1870s partly to slow typists down to prevent mechanical typewriter jams. And when we talk about software bugs, we are referencing a literal moth. In 1947, Grace Hopper's team found a moth physically trapped inside a Harvard Mark II relay. They coined the term because an actual insect was stopping the machine. Even the very first computer mouse, invented by Douglas Engelbart in 1964, wasn't sleek plastic or aluminum. It was carved out of wood.
And the physical footprint of this early tech was absolutely massive. In 1980, IBM released the very first 1 gigabyte hard drive. Notice that huge unit on the left? It weighed over 500 pounds and cost around $40,000. Today, you carry thousands of times that capacity on a microchip smaller than your fingernail. The contrast between the staggering physical weight of early storage and the totally invisible data we carry around today is just mind-blowing.
And this brilliantly illustrates the uniquely, hilariously human motivations behind some of our greatest technological leaps. The very first webcam wasn't invented for global communication or high-level security. No, it was created at Cambridge University by researchers who simply wanted to monitor a coffee pot. They were tired of walking all the way down the hall only to find the pot empty, so they rigged up a camera. So much of our modern digital infrastructure was built on exactly this kind of everyday, practical problem-solving.
Section 2. The first digital minds, the search for artificial intelligence.
That search officially launched in 1956 at the Dartmouth Conference. But think about it. How do you even measure a machine's mind? Early researchers constantly grappled with defining what intelligence actually meant. In 1950, Alan Turing proposed a foundational benchmark, the Turing test. It simply asks whether a machine can converse well enough to convince a human evaluator that it is, in fact, human. Interestingly enough, there is no strict universal standard for passing it, which made it just as much a philosophical test as a technical one.
And we saw the Turing test applied in surprising historical reality as early as 1966. One of the very first chatbots, a program named Eliza, was actually designed to simulate a therapist. By simply mirroring user statements back to them as questions, Eliza convinced some users they were talking to a real, empathetic person. It was a fascinating early illusion of intelligence.
Now, what is really interesting about this slide is that dramatic drop-off you see in the second bar. For decades, the hype surrounding early AI research vastly outpaced the actual technical results. This led to what the industry called AI winters during the 1970s and 80s. These were prolonged periods where funding completely dried up, all because the grand promises of thinking machines simply weren't materializing in the real world.
Section 3. Beating the grandmasters, machines taking the crown.
It wasn't until computing power finally caught up with algorithmic ambition that things truly began to accelerate.
And you know, the history of AI breakthroughs is often measured in board games. Back in 1997, IBM's Deep Blue defeated world chess champion Garry Kasparov. It was a massive watershed moment, the first time a computer beat a reigning human champion in a match. But the 2016 victory was arguably even more profound. DeepMind's AlphaGo defeated the world Go champion, Lee Sedol. This shocked experts worldwide because, as we noted earlier, the ancient game of Go has vastly more possible board positions than chess. More than atoms in the universe? AlphaGo couldn't just use brute force, it had to exhibit a real form of mechanical intuition.
Section 4. The modern AI explosion. GPT, AlphaFold, and beyond.
That breakthrough ushered in the era we are living in right now. To understand how these modern systems work, we have to look at reinforcement learning. It's a branch of AI that actually mimics how animals learn biologically. It operates on a strict sequential logic: trial, error, and reward. By letting a system try thousands of different approaches, letting it fail, and then rewarding it mathematically when it succeeds, the machine teaches itself optimal strategies that human programmers couldn't possibly hardcode.
And then we have GPT-style language models. Despite how incredibly complex they seem on the surface, their core mechanism is surprisingly straightforward. They read massive amounts of training data, learn statistical patterns within that text, and their primary objective is simply to predict the next word in a sequence. What is so remarkable about this is that this incredibly simple objective leads to surprisingly sophisticated, reasoning-like behavior.
This has led to absolute breakthroughs across the board. We've evolved from early consumer AI like the Roomba, which basically just used simple reactive algorithms to bounce off your living room walls, to things like DeepMind's AlphaFold cracking a 50-year-old biology problem by predicting protein structures with remarkable accuracy. We are seeing models exhibit emergent abilities, skills like arithmetic or translation that just appear suddenly as the models scale up in size. AI can now clone completely convincing human voices from just seconds of audio and generate brand new visual pixel arrangements from scratch. And now, multimodal chatbots can actually see and interpret visual images right alongside text. It's wild.
Section 5. The real cost of computing, powering the machine.
But all of this digital magic demands a heavy physical toll. So the crucial point is this: digital intelligence is not ethereal. It is grounded in massive, sprawling physical infrastructure. Training runs for large language models can consume as much electricity as thousands of homes use in an entire year. And the heat generated by these processors is so intense that data centers require massive amounts of water for cooling. So much so, in fact, that major tech companies now have to report this water usage in their corporate sustainability reports.
Section 6. Illusion of the machine mind. Pattern recognition versus consciousness.
Which brings us to a really necessary philosophical reality check. As these systems become more capable of generating award-winning art and holding deep, meaningful conversations, it is absolutely vital to understand what is actually happening under the hood. Despite the incredible hype, artificial neural networks are only loosely inspired by the human brain. They function very, very differently. Biological neurons are vastly more complex. The absolute limit of current technology is this: current AI models are brilliant pattern recognition systems, but they are not sentient minds. No system today possesses genuine understanding or consciousness. They don't know what they're saying, they only know the statistical likelihood that one word follows another.
Yet, as these systems master those statistical patterns, they're out here generating art, passing bar exams, and writing flawless code. Which leaves us with a lingering, deeply provocative question to close out this explainer. If a machine has no genuine understanding, what happens to our world when mere pattern recognition becomes completely indistinguishable from true human
Subscribe to
creativity?
40 Facts Daily and discover something amazing every day.